This is the design example 322 from the course text, and it involves a N-type MESFET um, transistor in the circuit. So you're given the biasing circuit, and you're required to find the circuit is to be designed such that for the given ID and VDS, you have to find the resistances. Okay, the unknown resistances are R1, R2, and RS. Okay, RD is given as 6.7 Ks. So the objective is to design the circuit with an enhancement mode MOSFET. Uh, so so consider the circuit in figure 65A over here. This is figure 65. N channel enhancement mode metal semiconductor field effect transistor. So the transistor parameters are given. The threshold voltage is 0.24 volts. Conduction parameter is 1.1 milliamps volt square. Modulation parameter is 0. That means the transistor again is an ideal. Okay. So we're not going to consider the forward resistance of the transistor. In the saturation, the current is independent of VDS. So the ID is independent of VDS. Then let R1 plus R2 is the constraint is as such that R1 and R2 sum of these two distances is 50 kilos. So you have to design the circuit such that VGS is 0.5 volts and VDS is given as 2.5 volts. So VDS is given as 2.5 volts over here. You can see the DC analysis that is done over here. So to start with, you see the analysis of MESFET, JFETs, MOSFETs. The DC analysis is very similar. Okay, in all these transistors and in their biasing circuits, you have to start with an assumption whether the transistor is in saturation or non-saturation. And for MESFET, these saturation current and voltage relationships, ID and VGS, are very similar to what we have in MOSFETs. The only difference in MESFET is that their VGS will be only held to a few tenths of volts. Okay, so other than that, as far as DC analysis is concerned, it's quite similar to the MOSFETs we have discussed in much details. So okay, now if you assume that this transistor is in saturation, then ID is given as Kn, conduction parameter, VGS, gate source voltage minus VTN. So we have the information of VGS. We know what VTN is and we know what Kn is. So Kn is 1.1 milliamp volt square. So you should plug those values over here for Kn, for VGS at 0.5 volts and for VDS 2.5 volts. And we assume that this current is the saturation current, that is, it is independent of VDS. So this VDS is somewhere passed beyond the saturation point. VDS sat. This point is VDS sat. So then you can use this relationship, okay, to find the current. And if you do so, you find out that this current is about 74.4 microamps. Okay, just plug those values, you find out the saturation current is 74.4 microamps. Then the voltage at the drain is you see that this the drain is clamped to 4 volts. Then you have this draw. There's a resistance at the drain which is taking the drop to the current 74.4 microamps. It is flowing through the resistance. So 4 minus ID RD is going to give you your drain voltage. Okay, 4 minus ID RD is your drain voltage VD. So this is written over here. VDD is 4 volts. So 4 minus 0.0744. This is in milliamps. 6.7 is in kilo ohms. So this is in volts. Okay, so VD is 3.5 volts. Then you know what is VDS. So VD minus VS is 2.5 volts. That is the difference between the drain and source point is 2.5 volts. Then you know what VD is. So you can find what VS is. VS is 3.5 minus 2.5 volts. So you have for VD as 3.5 volts over here. Okay, it's 3.5 volts. This is 3.5 volts. 3.5 minus 2.5 is your VS over here. So that is 1 volt. So now from 1 volts, you see this potential is at 1 volt. So 1 divided by the current ID, which is the same current that's flowing into the drain out of the source. It's the same current. Is you can find this by the ratio 1 volt over. So this is basically VS over ID. Okay, this is VS over ID. So VS is 1 volt. VS is 1 volt. 1 divided by ID is 0.0744. That gives you RS as 13.4 kilo ohms. So that is your 13.4 kilo ohms source resistance. Okay, so we have found one resistor. Then the voltage at the gate is, you know what VGS is. It's given as 0.5 volts. Okay, and we know what Vs is. So you can find the gate voltage. Okay, so the gate voltage is VGS plus Vs, that is 1.5 volts. Now, since the gate current is zero, there is no current flowing into the gate. You can apply the voltage divider. Okay, so voltage divider at the resistor R2. So the gate voltage is also given by the divider equation, which is given as Vg equals to R2 divided by R1 plus R2 into VDD, that is 4 volts. Okay, and this Vg is 1.5 volts, which we have already determined from the gate voltage over here. So just plug those values, R1 and R2, the sum is 50, which is over here. Okay, and this VDD is 4 volts. This gives the only unknown is R2, which is 18.75. So from this sum of R1 plus R2 50, you find what R1 is. R1 is 31.25. So we are done with all the restances. You have R1, you have R2, you have RS. Okay, assuming there is no gate current. The DC analysis is very similar to what we have done for the MOSFETs. Okay, so again, to check if this analysis is correct, you have to see if VDS is greater than VDS SAT, which is given by the overdrive voltage, the difference between the gate source voltage and the threshold voltage. The threshold voltage was given as 0.24 volts. So VGS is 0.5, 0.5 minus 0.24 is 0.26. However, your VDS is 2.5 volts, which is greater than 0.26 volt, which means that your VDS SAT was somewhere over here. Okay, let's say this is 0.26 volts, and you have biased your transistor at 2.5 volts. Okay, which is farther away from 0.26, which means the transistor is in saturation region. So indeed, the current equation that we used before was for saturation. Okay, this current IV relationship was for the saturation. So indeed, your transistor is biased in the saturation region. So the analysis is correct. So which confirms that the transistor is biased in saturation region. Therefore, the resistances that we found out are correct, and these are giving the saturated current of 74.4 microamps, which is flowing from the drain to source. Okay. So the comment is that DC analysis and the design of an enhancement mode MESFET circuit is similar to the MOSFET circuits, except that the gate to source voltage of MESFET must be held to no more than a few tenths of a volt.